Finding the mean for a set of raw scores is a pretty simple matter. All that we have to do to find the mean is sum up all of our raw scores and then divide by the number of raw scores that we have just summed up. And so for this particular list of raw scores over here, you'll find that the sum of scores ends up being 48. And so we would have 48 divided by 6 because there are 6 scores listed there. And this gives us a mean of 8. But what if I wanted to have the mean worked out for my z-scores? For the entire distribution of z-scores. So for my z-score distribution, or we could call this the standardized distribution. How would I find that? What would the mean of my z-scores be? Well, things aren't going to change. I'm still going to follow the same basic format, but I don't have a list of x values. I don't have a list of raw scores now. Instead, what I have is a list of z-scores that I can sum up. I'm still going to put this over n because the number of z-scores is going to be the very same as the number of raw scores. Every raw score has its own z-score. Therefore, if it was 6 for the raw scores, it's going to be 6 for the z-scores. So I really just need to find the sum of z. So to do that, I'm going to add up this column here. That will give me my sum of z. So let's do that. Negative 1.5 plus positive 1.5, that gives me 0. Add 1, now I'm up to 1. Take away 0.5, so now I'm down to positive 0.5. 0 doesn't change anything. Take away another positive 0.5, and I end up being at 0. So I've got my sum of z is equals to 0. 0 divided by anything gives me 0. And so I can say that my average, or the mean of my z-scores, equals to 0. Now this is true for this particular set of raw scores, for this particular distribution. I got a standardized distribution that had a mean of 0, a mean z-score of 0. But not only is it true here, this is always true for z distributions. No matter what set of raw scores you have, no matter what your distribution is of raw scores, once you convert your raw scores to a z distribution, the mean z-score will always be 0. So mean z is always equals to 0. So this is something you're definitely going to have to keep track of, that you're going to have to remember. So your mean z-score is always equals to 0. It's not just this one example that I've done here. So you can take any set of scores, as long as you convert every one of your scores to z-scores, not just some of them, but the entire distribution to a whole new distribution of z-scores, you will find that the sum of z comes out to be 0. Obviously, if I had only worked with the first few of these, it wouldn't have worked out to give me a sum of z equals to 0. But if I take the entire distribution, all of these cancel out to give me a 0. That's, in turn, going to put a 0 up top here. It's going to give me a 0 for the mean of my z-scores. Something else that's interesting to note is that, where do we see that happen? That mean is right here. I have a mean z-score of 0 right here. You're not always going to see a z-score of 0 in your actual list of z-scores. I mean, the average will always be 0, but you could have a different distribution where z looks like this. It's like minus 2 plus 2 minus 1.5 plus 1.5. Now, if you average these out, they would come out to be 0, but we don't see a 0 in here. In this particular case, though, we do see a z-score of 0, which is a good opportunity for me to show you that the mean score of 0 in the z distribution also happens to be equals to the mean of 8 in the raw score distribution. So the mean being equals to 8 corresponds, not surprisingly, to a mean in the z distribution equals to 0. These match up. wherever I have an average in my raw score distribution, that will automatically be a 0 in my z-score distribution. So the mean always, just like this is the mean z-score is always 0, the mean of a raw score distribution always has a z-score of 0. Really, these are just two different ways of saying the same thing.